Okay, I heard the exam was easy. What's that? See, I just got them today, so I will have a look, but maybe not before the PPIC event. Yeah, don't worry, we still have another exam and a final. It'll be all good. Okay, so I'm not gonna do recap. I just want to keep going. Every year I teach this class, I add material and I'm always behind. And I just realized that the last week of classes, we are shaved off because last day is on Tuesday. So we don't have the Wednesday. So I'm short basically 250 minutes like this. So I don't know how they did this to me this year, so we'll see. We'll go as much as we can. So that's why I'm moving presentations a little bit. So I moved the Monday presentation to Wednesday, and then I moved yours to 1 week, and I potentially might move the one after. Just want to make sure I cover the topic before you present on it. So we'll keep you posted. Okay, I think we stopped last time when we were talking about emulsions. So you all studied solubility and dilation so for the exam, so I'm not going to do a recap there. So emulsions and foaming, so this is the surface activity potential of proteins. So when we have aqueous and oil phase, obviously they are different in density. So there is high surface tension, so they would separate. In order to have them in a stable form mixed together as one phase, we need a surfactant or an emulsifying or a foaming agent if it's air and aqueous. So usually when we have an emulsion or foam, we have two phases. So you have the dispersing phase or the continuous phase, and then you have the dispersed phase. So that either oil droplets or air bubbles. So when you have a stabilizing agent, such as a protein acting as an emulsifier or a foaming agent, so the protein in naked form, if it's globular, it has to be flexible enough to unfold and orientate the hydrophilic portions to the aqueous and the hydrophobic components to the oil or the foam or the gas or air. So that's basically what it says here. In order to, form an emulsion, in this case here, we're talking about emulsions and then foam. When you want to form your emulsion, the first thing you want to do is you want to homogenize. So when you shake and agitate or homogenize, you will break the oil into droplets. If there is no emulsifying agent, what happens over time, you have phase separation due to density differences and interfacial stress. So what happens if you have then your protein is going to stabilize, form a film around your water or oil, depending if it's oil and water or water and oil. So the higher the surface tension, the more work you need to put in to homogenize and reduce the particle size. When the smaller the particle size, then it increases the surface area. So we add emulsifiers usually such as lecithin or phospholipids, mono and acetylglycerol, or proteins will serve as your stabilizing agents for the emulsion. Now, if we're talking about proteins, obviously. So you probably heard about hydrophilic hydrophobic balance, or sometimes it's called lipophilic hydrophilic balance. So LHB, that's the common term that you will hear usually, is having a balance between surface hydrophobicity and surface hydrophilicity. So if you have a protein that is hydrophilic on the surface and hydrophobic on the core, it's not going to adhere or absorb to the interface. So if you have a hydrophobicity that is low compared to surface hydrophilicity, you will have some adsorption at the interface, but not so much. So you want to have a protein that has a good balance between hydrophilic and hydrophobic. So you have quite enough of surface activity when you have a balance between hydrophobic and hydrophilic in order for the protein to adhere to the interface, to go to the interface and interact with both phases, oil and aqueous. So the first step is you want the protein to move to the interface. You want it to unfold and reorientate the different components, and then form kind of a film, interact with each other and form a film around your oil droplet or water droplet, depending if it's oil and water or water and oil. So there are different factors that contribute to emulsifying or emulsification, the intrinsic and extrinsic factors. So intrinsic factors has to do with the protein characteristics, surface hydrophobicity, how flexible the protein, able to unfold, orientate its different components to the different phases, how much charge or hydrophobicity it has, is the protein soluble or not soluble, and what dictates the structure and conformation obviously is the primary structure or amino acid composition, and whether or not the protein is denatured. So these are characteristics that are intrinsic to the protein that will impact emulsification. And we have two types of proteins. You have the open structure proteins such as caseins, and you have the globular proteins such as whey protein or plant protein. Flexible proteins are naturally better emulsifiers. So we think about casein, it has an open structure, it's flexible, it has quite a bit of surface hydrophobicity and hydrophilicity. So it has a very good balance. So it has very good emulsification capacity. So we'll talk about more casein more later on. Globular proteins, they form dense films. Why? Because they're smaller usually than open structure proteins. So you can have more of the globular proteins on the surface. So you can form a thicker film. So they might have less emulsification capacity, but they will have better emulsification stability because they can form a thicker film around your oil droplet or water film. A mixture of both will be great to have this flexibility so that the quickness of forming the emulsion, the ability to form the emulsion and emulsify a larger amount of oil or water in oil. But at the same time, you want that stability to avoid coalescence and phase separation. Extrinsic factors, obviously temperature, pH, and ionic strength. So sometimes you want to denature the protein a little bit so that especially if it's globular protein, so heating the protein a little bit can help. You don't want to have high pH or low pH because you don't want the protein to be too charged, then you won't form the nice film and get the nice interactions between proteins to form a film around your oil droplet. So you don't want a lot of repulsion. So, but also if you have a pH close to the isoelectric point, that's also not good. Because then you don't have enough charges, you have a lot of protein-protein interactions, you have aggregation rather than the balanced formation of the oil droplets or the film around the oil droplets. I mean, I just want to elaborate visually what I'm talking about. So you want to think about your proteins forming a film. So individual molecules of proteins forming a film around your, let's say you're having oil here and then water. And then you have another oil droplet and another oil droplet. So when we say we want a balance, you want the interaction between the proteins, among the proteins, on the film. But once a film is formed, you also want to have repulsion between the proteins on the surface of each droplet. If you have repulsion, then you will have stability. Okay, so we don't want to have a pH that is close to the isoelectric point, because then you would not have enough repulsion. You don't have enough charges, so you will have phase separation, and you will have more aggregation rather than formation of the film. Aggregation forming out of solution. So the pH has to be ideal to establish the formation of the film, and at the same time have enough repulsion between the oil droplets so that they don't coalesce and have phase separation. Okay, so that's why this hydrophobic hydrophilic balance is important, because you need some interactions and you need some repulsion. So every protein is different, so the pH is not the same for all types of proteins. So we need to select the ideal pH for the type of protein that we're working with. So we want to be away from the isoelectric point, but at the same time, we don't want to be at a pH where we have a lot of charge and a lot of repulsion, rather than the desired interactions that allow us to form the film. Sometimes salt is also important, salting in, salting out effect, and finding the balance where the salt can help with inducing some solubility, but at the same time enhancing protein-protein interactions to form the film. So it's complicated, but for every protein, we need to find the balance. We need to find the right conditions that gives us the formation of a stable emulsion. Processing parameters, so homogenization, how much work we need to do to get the emulsion formed. And with homogenization, sometimes you hear first stage, two-stage homogenization forming a coarse emulsion versus forming a fine emulsion. The finer the emulsion, the better is the stability, or the longer is the stability of the emulsion. Because when you have fine emulsions, that means you have very small particle size of the oil droplets. Or the smaller they are, the larger the surface area you have, and then you would have the better stability of the emulsion. If there are big oil droplets, then you will have fluctuations sooner, and you'll have coalescence. That means when the two oil droplets join, you will have a bigger oil droplet. So the smaller the oil droplet, the finer is the emulsion, the longer is the stability of that emulsion. Presence of surfactants. If you have surfactants and you have proteins, the surfactants, the small surfactant molecules, will displace the proteins on the interface. They are smaller, they reach the interface quicker, so they might displace the protein. And if they displace the protein, since they are smaller, they might form thinner film. And if you have thinner film, you have less stability of the emulsion. So you also want to strike a good balance between whether you're going to use small surfactants, or if you have protein, you don't want to have that counter effect on the emulsion stability.
Yeah, what is done by surfactants?
Huh?
What do you mean by surfactants?
Surfactants are substances like lecithin. So like phospholipids, for example, monoacylglycerols, these are emulsifiers of small molecular weight. And this, I think the name surfactants come from being surface active and at the interface, stabilizing the emulsion. So the process that is involved in formation and stability of the emulsion, you have, first of all, how quickly the protein can move to the interface between the oil and the water. How much protein is absorbed at the interface? How many molecules of proteins we have that form that film around the oil droplet or the water droplet? How much the protein is able to orientate itself efficiently to the hydrophobic to the oil and hydrophilic to the water? And how much is the protein capable in reducing the interfacial tension? So once the oil droplet is formed, how much the protein is able to keep that phase integrated rather than separated? The higher the tension, the higher the rate of separation or rate of healing. And the ability to form a cohesive interfacial absorbed protein layer or the cell. Okay? So these are the kind of characteristics, we call them the processes that gets allowed the protein to form the emulsion and then to stabilize the emulsion. So when we have two phases of different density, without a surfactant or an emulsifying agent, you will have things separate. But once you have the emulsion form, it's not stable forever. Over time, you're going to have fluctuation initially, and then coalescence, and then phase separation. So there are different characteristics that extend the stability of the emulsion. We talked about droplet size, density difference, the density of the two phases, the viscosity of the continuous phase. They're all important, and there is an equation that relates all of them together. So V here is the rate of cleaning. R is the radius of the oil droplet. G is centrifugal force or gravitational force. And the change in P, that's the or the difference in density. And then the mu here is the viscosity of the continuous phase. I think they're all labeled here. Okay, so the larger the radius of your oil droplet, the larger is the rate of separation. So V is the rate of cleaving or separation. The higher the gravitational force, the higher is the rate of cleaving. The higher the difference in the density of the two phases, again, the higher the rate of cleaving or phase separation. And then the higher the viscosity, it's an inverse relation. So this is over the viscosity. So the higher the viscosity of the continuous phase, the slower the rate of separation. So that's why sometimes the proteins play a dual role. One, the protein forms the film around your oil droplet, and then the rest of the protein that is not on the surface or at the interface is increasing the viscosity of your continuous phase. And with the higher viscosity, your oil droplets are more to stay put rather than fluctuate, coalesce, and separate. So here's just saying that the proteins, if they are larger, they are able to form a gel or have gelling ability, that means able to form interactions and form the film. So that has good viscoelastic properties, so that will enable them to form a nice cohesive elastic film. And the dissolved proteins add to the viscosity of the continuous phase. Any questions there? We can ask questions. Okay. So here's linking a little bit structure to function. Mentioned KCE earlier. This is the KCE has an open structure. Just to remind you, with the random structure being due to the high percentage of proline, which is structure breaker or secondary structure breaker. So it's a flexible open protein, naturally open, very antipathetic. That means it has really high surface hydrophobicity and high charge on the surface. So it has a very nice balance between hydrophobicity and hydrophilicity, and that is why we call them natural emulsifier. We have many of you have been doing emulsification capacity in the lab. We haven't done necessarily KCD, at least not this group of people. But when we're doing emulsion, you only need about 0.5% protein when you're using KCD to form a stable emulsion. So the emulsification capacity is for KCD is about 1,800 grams of oil per gram of proteins, which is very high. It's the highest that you ever worked with, those of you that did emulsification capacity. And at a very low, relatively low concentration of the protein. So, but if we look at plant proteins, there are these big globular proteins, high quaternary structured proteins that are very hydrophobic on the surface. They require to be partially unfolded in order for them to form an emulsion where you expose some of the hydrophobicity, but also some of the hydrophilicity is needed at the surface as well, and we need some flexibility of this protein. So we need some form of manipulation. Nevertheless, we require at least 1% protein solution in order for it to emulsify. So it's not as flexible and fast moving to the interface, doesn't have that big of a capacity. So therefore, we need at least 1% protein when we're working with soy, and pea is even worse. We need about 2% protein. So soy does emulsify well, but not as good as casein, and we need at least double the amount of casein in order to form the emulsion. For pea, well, this is an old pea protein ingredient. Some of you are working with a newer ingredient that has better emulsification, but most of the time we need at least 2% protein, and the EC emulsification capacity, it's not that great compared to casein.
So how did we, what did we do to make sure?
Huh?
Did we do anything to treat it or to let it unfold?
What do you do when you do the ECM in practice?
Well, just a few.
But what do you do to form the emulsion? Yeah, now, so that's physical denaturation. Yeah. Still, with that physical denaturation, you don't break that sulfide. And you have some proteins, the globular proteins in RNS, they're stabilized by disulfide. Casein do not have disulfide in them. They're more flexible. So they are easier to orientate their different components to the oil phase and the water phase. Even though we nature those plant proteins with homogenization, they're not as flexible as the casein. So therefore, you don't have as much emulsification capacity as the casein. Other questions there? Okay. So many of you are familiar already with emulsification capacity. It measures the amount of oil that can be emulsified by a gram of protein. So the way we do it, or you do it in the lab, is you titrate oil at a specific speed as you are homogenizing your protein solution. So oil goes in at a specific speed while you homogenize to form your emulsion. The emulsion is formed, it's a thick emulsion, hopefully not all proteins form nice thick emulsions. And you continue the titration, the oil keeps going in drop by drop until you have a phase separation. That means you cannot emulsify anymore, and then the emulsion is broken. And you stop the titration at this point, and you calculate how much oil you convert the volume to weight, and then you calculate per gram of protein. So that's how you determine emulsification capacity. Emulsion stability can be done in estimated in a method that you all love or hate. It's a very annoying method of determining the emulsion, but we have to figure out a way to determine emulsion stability in a short period of time so that you don't have to wait days or weeks to determine the emulsion stability or predict the emulsion stability using different types of proteins. So we use this assay where you prepare a protein solution. I'm not sure these numbers are correct, but you prepare a protein solution, you homogenize it with oil. Don't know if you use sodium, use so with oil, and then you add SES, and you take absorbance at time 0 and absorbance at time 10 minutes, and that means gives you the phase separation. I think the more the change, the lower is your emulsion stability. The more the change in absorbance over time, the lower is your emulsion stability. However, the best way to determine emulsion stability is to actually form an emulsion and let it store and look at physical characteristics of the emulsion over time. So one thing we do to evaluate emulsions is also looking at the zeta potential of the emulsion itself, because this gives you the charge on the surface of the oil droplets. The higher the charge on the surface of the oil droplet, the more repulsion you're going to have between the oil droplets, and the less fluctuation, less coalescence, and less cleaning. There is about, they say anything of 35 or maybe negative 30 and more of the net charge, the better is the stability potential of your emulsion. We also measure turbidity over time. As turbidity increases over time, that's an indication of fluctuation and coalescence over time. In this example, we actually prepared an emulsion containing different types of whey protein sources. And we stored the emulsion in the incubator, but we did accelerated storage. We stored it, I believe, around 40 degrees C, 45 degrees C for 10 days. And we did measurements of the zeta potential, the turbidity, but also particle size. So when we looked at changes of particle size over time. So the solid line is 0 time, and the dotted line is after 10 days. And this is the distribution in size of the oil droplets. So one of the formulations produced after 10 days, you get this spread of molecular size that increased in size. So that means your oil droplet coalesced and increased in size over time. Other types of proteins we've used, the particle size distribution remained constant over the 10 days of storage. This is the better way of measuring emulsion stability, but when we are comparing different proteins and we just want to look at estimation of emulsion stability, then we do the ESI and emulsion activity assessment that we do in the lab, which is a quick assay. It gives you not the exact emulsion stability of that protein, but at least gives you comparative between different types of proteins that are all measured under the same. But this would be the better way of measuring emulsification stability of a true emulsion. We can also look at the morphology of the emulsions over time. So this is an example of cheese. Cheese is an emulsion. You have your fat that is stained red, and the green is your protein. And then here you look at the morphology of the emulsion. You have nice distribution of oil droplets, very nice film of the protein that is causing the entrapment of these oil droplets and preventing phase separation. This is done by CLSM, that we use confocal laser or light scattering microscopy. Here is the emulsion example that we did with pea protein, looking at the impact of whole plasma. And then what we did is looking at the morphology at day 0 and then morphology at day 10 to see what happened to our fine emulsion. We produced fine emulsion using two-stage optimizer. So you have day 0, you see the protein dispersed, your oil dispersed nicely. And then after 10 days of the commercial PPI produced emulsion, we see aggregation of the protein and larger oil droplets forming over time. Whereas the plasma treated samples, the emulsions stayed more or less the same over time. We had better stability of the emulsion over time. So there are different ways of assessing the emulsion stability, but it's always better to have an actual emulsion and look over time in order to assess the actual stability of the emulsion. Foam, I'm going to go over this very briefly. You have similar concepts where your hydrophobic components of the protein will orientate itself through the air, and then the aqueous phase, you have the hydrophilic component of the protein orientated to the aqueous phase. So these are the two phases in foam. Again, information of the foam, you would also want to have that protein is denatured. So when you form the foam, there is beating or air injection. During that, your protein is opened up, and then you would hope for some flexibility for that protein to orientate the different components of the different phases and form a film around, in this case, the air bubble. So different types of fluids are natural foams, pure marines, and then the sponge cake. These are foams. Ice cream is a foam, it's an emulsion and a foam. So what happens again, you form a film around the air bubble. Again, you have your proteins interacting at the interface, forming a nice thick film. And then you count on a disjoining pressure. That means you want to have electrostatic repulsion, you want to have static forces that prevent these static forces. You know what static forces are? Yeah? Are you familiar with the remote? I didn't want to say static forces. It's okay if you don't know. Huh? Static hindrance, static forces. So when you have bulky groups, they kind of prevent each other from coming closer to each other. So static hindrance due to the bulkiness of a component. So static forces or static hindrance, electrostatic repulsion, van der Waals repulsion will cause these air bubbles to be separated from each other. we call this joining pressure. The more charged the protein is, the better it's going to cause that repulsion. And the more protein you have at the interface, the thicker is the film, the more stable is your film. Now, the viscosity is very important of the continuous phase because you have capillary forces that might cause this liquid between the two bubbles to thin out. If that liquid thins out by capillary forces, then the bubbles will come together and will form bigger bubbles, and you lose the stability of the foam eventually. So what reduces this capillary force drainage is the viscosity of the continuous phase. So if you have good concentration of protein that is soluble, not aggregated and precipitated, soluble protein in the continuous phase that will add the viscosity, enhance foam stability. So we measure foaming capacity, the amount of foam used per gram of protein, and we can measure that also by measuring the overrun, percent overrun, means the volume of the foam minus volume of the initial liquid. So that means how much air was incorporated over the volume of the initial liquid. Stability is after a certain period of time, you measure the foam volume again, and that will determine the decrease in foam over time, gives you an estimation of the foam stability using different types of proteins. So with that, what we covered so far, we talked about intrinsic properties of protein, that forms the structure, how structure is impacted by different external factors, and talk about functionality. Next, we will be talking about different sources of proteins, daily protein, legume proteins, cereal proteins, egg proteins. I never make it to eggs by this point. I hope I can make it to cereal protein. So, but before we go into the different sources of proteins, I want to cover a very important topic, enzymes, which are important in food science, and they govern a lot of functions. So I want to switch gears and spend time on enzymes. Any questions before I switch gears? So what's the best thing to do? Huh? Stability is important, but what can we do if we want to use less emulsifying agents? Because sometimes you want to reduce costs by using less of the expensive ingredient. So what do we do? Then we lose on stability. We mix. There's never a clear winner. We build on synergy of the proteins, right? So we put them together. Yeah, good question. Maybe stole one of my exam questions. Why is zeta potential always negative? Is it always negative? Is zeta potential always negative? Who's going to answer this question? It's a good question, but is zeta potential always negative? No, why not? Depending on pH. Hold that thought. So the zeta potential is dependent on the pH of the system. And different proteins behave differently at different pHs because of the different amino acid composition. So when the pH is above the isoelectric point of the protein, what would be the charge of the protein? When the pH is above the isoelectric point of the chart. When the pH is below the isoelectric point, positive. So the zeta potential that you saw that I reported here was at pH 7. And for whey protein at pH 7, it's negative. Thank you for that question. That's a good question. Yeah, so zeta potential, what we do in the lab, we usually measure it at pH 7. But if I'm interested in looking at the beverage application at pH 3.4, which Ali will be doing for her glycated protein, she's going to measure zeta potential at pH 3.4 and zeta potential at pH 7. Write that down. Okay. All right, so I'm switching to my next favorite topic in the world, enzyme. That's not my favorite topic in the world yet. Wait. Where's the enzymes?
Right there.
There.
Graham, I have a quick question for
You have a question, yes.
Sorry. So on our problem set, you asked if we would want to choose, one that has better, emulsifying capacity or stability, and it just depends what we want to use it for, is the answer.
Which one, which
Yes.
question was that?
This is problem set 3.
Yeah, so what was the question?
You asked if we would choose an ingredient that has better emulsification capacity or stability. And so
Yeah.
the answer is just, it depends on what we want to do with it.
No,
It's,
well, it depends what, but do we want one better than the other?
it says the choice between wanting higher capacity versus stability will be based on the application, storage time, and processing conditions.
So it depends on the conditions, but also it depends on which proteins are we working with, and also if we can blend them, then we should blend the different proteins.
And I have a question. So if the value of zeta potential is more than -30, so
If the value of zeta potential is what?
more than -30,
Yeah.
so it has a good emulsion capacity.
Are we talking about the zeta potential of the oil droplets on the surface of the oil droplet, or are we talking zeta potential on the protein itself?
So I just need to understand if we get the value more than -30, so does it apply for all the proteins? Like it has more emulsion capacity or?
It's not capacity, stability.
Stability, sorry, stability.
So usually if you have zeta potential higher than -30 or -35, you will have good stability of the movements. Yeah, but that's kind of like not rule for everything, but that's what usually is an average. So the higher but you don't want to have also very high charge because then you don't form a film around the oil droplets. So there's always a balance, but yes, the average is between -30 to -35 is what is important. Yeah. Okay, other questions? We have 4 minutes before a break, so. All right, let's answer.
It's only A.
Only A. None. She looked ahead. Huh? So are enzymes proteins? Are all enzymes proteins? Are you 100% sure that all enzymes are proteins? Let's answer this question together in a little bit here. Okay. So enzymes are made of amino acids only, not always. So they can have different components associated with them, coenzymes or cofactors that are needed for the substrate to bind. So they are not necessarily only up amino acids. So these are different, naming for the enzyme. So if you have an apple enzyme, so that's your protein portion, the substrate will not bind to it as such. Needs the coenzyme. When you have the coenzyme, then it becomes a whole enzyme. And then after that, the substrate can bind to it. But not all enzymes require a cofactor. Some enzymes do require a cofactor. This is your favorite part of enzymes.
So the answer was neither. None of them.
Do you want to know the answer? You have to wait until I talk about. Yeah.
Okay.
Okay, so here, what is KM?
Michael's mental constant.
Yes, exactly. It is the Michaelis mentioned constant, KM. All right, what does it represent? It's correct, we named it, but what does it represent?
Enzyme activity.
No,
Is it the rate of?
it's not a. It's a constant,
Is it the energy required to activate the enzyme?
no. It's okay, you don't, that's why we're covering this class, because you guys forgotten about KM. Yeah, Genchem only, I covered it somewhere else. You took my class. Oh, I'm sure you did. Yeah.
Velocity of the reaction.
It's not a rate. It's a constant. You tell me.
But I think, okay, I'm guessing is it the activation energy to.
It's not an energy, it's not a rate.
It's not.
You tell us.
Isn't the rate constant what's here?
It's a constant, but it's not a rate constant.
Like the minimum amount of substrate needed for,
It's getting
reactions to happen.
It's the concentration of the substrate at which the velocity is Vmax over 2. That is the max. Okay, you expect us to know this? It's an important parameter in the enzyme world, and we are going to talk a lot about Km. It's the concentration of the substrate at which velocity is Vmax over 2, half the maximum velocity basically. So it's the concentration of the substrate. So it's not the rate. It's the concentration of the substrate at which the rate of the reaction is Vmax over 2, half maximum velocity.
So is it kind of like, pKa?
pKa,
Circuit away.
no, it's actually just the concentration in a molar concentration. It's the concentration of the substrate at which your rate of the reaction is half the maximum possible. Yeah, we will spend quite a bit of time on it. So if the concentration of the substrate, that the answer was in the question. If the substrate concentration is much greater than Km, which of these now is correct? You have very high concentration of substrate and above Km by a lot. Which of this is correct? Is it B? What? You're guessing at this point. A.
Hang on.
You think B? Yes, you are correct. So when the reaction is saturated with the substrate, that's what it is. So when your substrate concentration is greater than Km by a lot, that means the reaction, the enzyme has a lot of substrate to swim with. So you are saturating your enzyme. So now the reaction is not dependent on substrate concentration anymore. The reaction is dependent on the concentration of the enzyme. So it is zero order with respect to the substrate, but first order with respect to the enzyme. If you increase the enzyme concentration, then the rate of the reaction will be impacted. That's what first order means. That means the rate of the reaction is dependent or changes with the concentration of the enzyme. But at this high concentration of substrate, then the rate of the reaction is not impacted by the substrate anymore. It's zero order with respect to the substrate. All right, so when we are measuring, when we're using an enzymatic reaction to measure, you're measuring proteases, right? Not really. You're measuring proteases, correct? Yeah. What do you want to have? You want to saturate the system with the substrate, or you want to have low concentration of substrate? You are looking at enzyme activity.
Probably more substrate, right? Students and reaction.
Yes, so you want to saturate so that you can measure enzyme activity. So any change in your enzyme concentration is going to affect the rate of the reaction because you're measuring enzyme activity. So when we're measuring enzyme activity, we need to make sure that the rate of the reaction is not dependent on the substrate. You flood the system with substrate. You want to make sure you have a lot of substrate in the system so that you can detect any difference based on enzyme concentration. The other hand, if you're measuring glucose, so you want to set up your reaction where the concentration of your substrate that you're trying to measure is much lower than Km. When you do that, then, and you keep your enzyme concentration constant, then you can detect a change in glucose concentration. Then it would be first order with respect to substrate, zero order with respect to enzyme. So that's why enzyme kinetics is very important. You need to know Km of every enzyme and substrate combination. We need to know the Vmax so that we can set up the reaction parameters. If I'm measuring substrates, I want to make sure I am having first order with respect to substrate. If I'm measuring enzyme, I want to make sure that the reaction is set up in a way that it's first order with respect to the enzyme. So that's one reason why we study enzymes and want to understand enzyme kinetics. So I'm going to give you five minutes break, only 5 minutes break, because I have to continue a little bit here and then hand the floor to our presenters today.
Yeah, I think we know something.
Hmm. Oh, man. I forgot to print the presentation evaluation forms. Okay, I'll be back. I need to print presentation evaluation forms for your presentation. My brain today. Okay, you have extra 5 minutes.
Because it's so like, what are we gonna, what's Emily doing with Chris? Yeah. Like you didn't say what we were gonna do. Oh. You're like, I have some big. No, because I know what it is. And if I was. For Emily. Stop here. And then putting together a collaboration. No, I just like. I have there. Yeah. Did you want to talk?
No, yeah. Yeah. It's good to be back. Okay.
Wonder if they have like.
Okay, let me know when you guys are ready.
No,
Can you go to your object and go to canvas? And under presentation, if you click on that folder, you'll find the presentation evaluation form. Think about 20 copies. I can continue until we have that. I'm sorry, I know you guys are waiting to present and be done with it. But it shouldn't take us more than 10 minutes. You know what, which form I need, right?
I'll pull it.
Yeah. So. All right, hang in there, you guys. Okay. All right. So can we list some application of enzymes in food systems? General, what do we use them for? Yeah.
Where lactase breaks down lactose and extreme to reduce.
Processing tools. Yes. Processing tool using lactase to convert lactose for lactose intolerant people. What else? That's processing. Yeah.
It's digestion that is that, they got spot next.
That's inside our body, but for food, we can use enzyme to produce protein ingredient hydrolysates that have different functionality. Again, processing tools. Okay, this is all processing tool. I got it. Another use.
Well, not a use, but
But-
the we have to worry about is it, is a spoil or a mechanism. of
Quality. So food quality, presence of fly phases and off flavors that could happen Yes, quality, processing tools, quality, protein quantification needed, like ELISA, specific peptide. Analysis, we use enzymes in analysis, either like in ELISA or used to quantitate components like glucose, total starch. What else?
I think it's related with the plant growth for the defense system.
And growth.
Like the algorithms in general, they're important for the growth of the defense.
Food systems.
Right?
Food system, yeah, of course, enzymes have a lot of activity benefits for us, for the plants, yes. But food system, so far, we talked about quality, processing, use in analysis.
You say sensory, like the pineapple has, what is it, bromelain? Yeah, I'm going to.
Bromelain doesn't make your tongue tingly, the enzyme, it's actually, it's a protein. So what the hell?
Maybe like for like maybe new food products.
Yeah, processing, yeah. Huh?
I don't know.
Food safety.
Enzyme, you know.
I'm not sure. Food safety. Okay, so sometimes to manage waste, you add enzymes so you can hydrolyze, let's say if you have it, you have a lot of sugars or proteins or fats, so you put enzymes to break them down so they can drain better for waste management. You measure enzymes, for example, to like oxygenases to test pasteurization, for example, or to determine an activity of an enzyme to know how much you want to put in let's say milk to produce cheese, how much rennet is needed. So I need to do enzyme activity on that rennet that I'm using so that I know how much I need to add in the batch of milk. Okay, so quality, where enzymes can cause problems, so we want to measure their presence, their inhibition, where they use them a lot to process foods. You guys gave a lot of examples. Waste management, quantification, measuring activity of different enzymes, the good ones and the bad ones, and to determine how we're going to inhibit them, if we need to inhibit them, like polyphenol oxidase that cause a lot of problems for browning. So a lot of uses. So we need to be able to understand their kinetics. We isolate enzymes, we characterize them to understand their affinity for different substrate, their optimum pH, optimum temperature, what's their maximum velocity at specific concentration of substrate, and so on. So we really need to understand enzymes in order to be able to apply them or measure them for different purposes. So what's the definition of enzymes?
Protein noise activation when you required for reactivities.
Yes, so they're biological catalysts, basically. So they are catalysts, biological catalysts that lowers the activation energy and speeds up a particular reaction. And convert substrate or substrates to different products, and then you get the enzyme back to be reused in the reaction. It's not consumed in the reaction, it can be freed and reused. Okay, are enzymes proteins? Is the big question here. Before the 1920, that's over 100 years ago, before 100 years ago, they were generally thought as they are. And then there is a smart scientist, a German scientist, in the 20s, over 100 years ago. He and his group were able to isolate peroxidase, the pure solution of peroxidase. They measured protein in that solution, and they found no protein in the solution. They found zero protein in the solution. And then they said, well, enzymes are not proteins. An American scientist from Cornell University isolated urease and crystallized that urease enzyme and turned out to be protein. There are a lot of back and forth between these two scientists, and you can imagine the European community, who did they side with? The German scientists. But who won? The American scientists. Why did this guy and this group could not have protein in their solution? It's of knowledge. Huh? Lack of knowledge. Lack of knowledge? Huh? You know that enzymes are active at a very, very small concentration. So the method that you used for detecting protein was not sensitive to detect the amount of enzyme in that solution. So they're smart people, but their method for detecting protein was not sensitive, and they assumed that if there's no protein, there's no enzyme. It's not enzymes are not protein. But then these guys came along and they said, hold on, have you heard of ribozyme? Yes. What are ribozymes? There are biological catalysts, there are enzymes in the body, in the cells, that catalyze biological reactions, but they're not proteins. So they're nucleotides. So basically, not all enzymes are proteins. These guys won Nobel Prize for the discovery of ribozymes that they have the catalytic activity of forming a peptide bond or doing different activities in the body, physiological reactions similar to the proteins enzymes. But food enzymes are all proteins. Okay, so not all enzymes are proteins, but all food-related enzymes are proteins. Okay, then. That settles it. Okay. All right, so I hope Chris comes soon for you guys, for your own sake. So purification of enzymes started as early as in the 1930s in order to characterize them, understand their activities, and understand their mechanism of action. So it started early on by purifying using chromatography, different forms of chromatography, electrophoresis, or solubility-based assays to purify the enzymes, characterize them, and then discovery of them. Over 3,000 enzymes have been categorized, purified, characterized, and given names. So the structures of enzymes, including primary structure sequencing. The sequencing can be done using gene sequencing, the encoding of the proteins, or by molding, and looking at the secondary and tertiary structure by NMR, and figuring out how big they are, whether they are homogeneous only in the of amino acid, or whether they are heterogeneous, having other components than amino acids. And then also figuring out synthesis of enzymes. Now, the enzyme nomenclature is done by the enzyme commission. So every enzyme usually have an EC number, enzyme commission number. I'll finish this slide and then I'll hand it over to you guys. So enzymes can be given trivial name or common name like trypsin, terpene, pepsin, bromelain. So all of these enzymes, or they can be given systematic name that has the name of the substrate in it, like lipase, for example, lipid hydrolase. So it hydrolyzes lipids. So lipase or triacylglycerol lipase. So name of the substrate in the enzyme name and the use of A's at the end. And also based on the reaction that they catalyze. So there's 6 types of reactions. So the one that is oxidation reduction, so an example is catalase or peroxidase, hydrogen peroxide oxidoreductase, catalase or peroxidase. Hydrolysis, breaking down the bonds and releasing water. That's why it's called hydrolysis, release of water. So hydrolases. Transferases, transferring of a functional group from one substrate to the other. For example, transfer of phosphate group. Breakage or formation of double bond. Lyases. Another one is isomerase. Isomerase, for an example, is using producing high fructose corn syrup. So basically, you have a starch to convert to glucose, and then you use isomerase to convert glucose to fructose. And then the ligase, which is basically forming a covalent bond between 2 different substrates. These are the examples of using the name of the substrate with the function associated with it. So triacylglycerol acyl hydrolase, so that meaning it's in short lipase with breaking the lipid and releasing H2O after water. This one is oxidizing this, the use of hydrogen peroxide to catalyze an oxidation reaction. And here, D-glucose phosphotransferase transfer the phosphate from one group to the other, or glucokinase. So what you want to remember, the 6 different types of reactions that enzymes catalyze and how the naming is done. Okay, so I'm gonna stop here and allow the group to present to you. So that means we're gonna stay 10 minutes extra today, and that is my fault for not thinking ahead of time. You don't use my computer because I'm recording.
Oh, well, we had made a few like presentation note updates, just like in our personal notes.
Do you wanna
So you want to
email it to me?
Yeah, I can share this with you. Yeah, or do you want to email those a PowerPoint or as a Google Slides?
Whatever you want, just,
Google Slides.
and do you wanna give everybody one of these, please?
If you send it to you in your email as a Google slide. Oh. Thank you.
So while we get this done, so you're going to evaluate the group. Write the names of all the presenters. We have Saj, Yi, and Anastasia. There's a section where you're evaluating them as a group. And then the lower part is evaluating each person individually. So make sure you write the name and then add up the score at the end. Presenters, Saj, Yi, and Anastasia, you're also going to grade yourself. So you're going to also, at the end of the presentation, take a sheet and write your name at the bottom. Because part of your weight of the grade will come from how you typically grade yourself. Each of you guys, especially the ones registered in the class, you want to write down at least a question or 2 to ask the presenters. They are going to be graded on answering questions, and you will be given +2 obviously for asking a question. So I expect each one of you to prepare a question or 2, but we might not have time to all of you ask your questions, but we need to be ready with meaningful questions. Okay. these presentations reinforce the knowledge that we learn in class, so please give them your fullest attention and utilize the knowledge to apply in exams and the final. So do you want to present directly from here?
Yeah.
Okay,
You can go there to slideshow. Not there, right here.
yeah, but I want to put it over there.
Yeah, I can set it for you. Okay, I practice this.
You practice.
Well, not.
Yeah.
And then go to slideshow.
You can,
Oh, you got, okay.
you got it. From here, right?
Yes, I got you. Oh, it's like, okay. Bring the mouse back, here we go.
Thank you, Chris. Save the day.
All right. When do we want to, maybe one other way, but we'll just do introductions. Okay, guys, ready?
We are ready.
You're not ready for this. Okay, here we go. Hi, everybody. My name is Sajwa, and today our presentation is on the comparison of extraction methods for pea protein isolate and their impact on structural and functional properties.
Hello, my name is Anastas.
All right, let's get started.
As introduction. Okay. Growing interest in pea protein. There is growing demand for proteins, especially protein from plant sources. Pea protein has the potential to address limitation from soy protein because first it is non-GMO, it is currently low agenicity, environmental benefit that promote sustainability. Let us talk about pea protein. Scientific name is Pisum sativum. Legumes consist of two classes of protein, albumin and globulin. Albumin are primary structural protein or enzymes and make up between 10 and 40% of the total seed protein on average. Globulin, on the other hand, are storage protein, and that comprise 40 to 90% of the total protein. They are salt soluble and are important for protein functionality. Globulins can further be classified based on their segmentation coefficient, with the main two fractions, 7S glycerin and 11S globulin.
So 3 articles will be introduced in our presentation, which cover 4 extraction method. Ultrasound assisted alkaline extraction will be introduced in Article 1, and we will mention the micellar precipitation in Article 2. Alkaline extraction and salt extraction will be covered in Article 2 and Article 3. To evaluate the extraction methods, the selected structural and functional properties in each article will be introduced. We will have conclusions for each articles and overall conclusions at the end of our presentations. Talking about objectives on each paper, the Article 1 is to optimize the ultrasound-assisted alkaline extraction of pea protein isolate for maximizing the extraction efficiency, and also to investigate effects of the method on protein structure functional properties. The Article 2 is to investigate the structural and functional properties for different pea cultivars using alkaline salt extraction and micellar precipitation. The Article 3 is to evaluate the pea protein extraction conditions to maximize the product purity and yield using alkaline and salt extraction to characterize the impact of 2 extraction methods on protein structure and functionalities, and also to translate controlled benchtop extraction conditions to pilot scale production of pea protein isolate and to evaluate the impact of scaling on structure and functionality of the pea protein. So now let's take a look at our first article, an efficient ultrasound-assisted extraction method of pea protein and its impact on protein functional properties and biological activities. From the table 1 on the left, we can see that the authors have 4 variables for the experiment: the solid liquid ratio, pH, ultrasonic amplitude, and extraction time. They tested different sample concentrations with solid liquid ratio from 1:6 to 1:12 gram to ml and pH from 8 to 10. They also tested sample at different ultrasonic amplitude from 25 to 35% and extraction time from 5 to 15 minutes. To determine the optimized extraction condition, the box banking design was used. Basically, the pea powder was solubilized in the DI water at different ratio and adjust to different pHs. An ultrasound was applied. After extraction, the solution was adjusted to pH 4.5 for protein precipitation. The precipitated protein was collected after centrifugation and dissolved in the water of pH 7, and the pea protein was freeze-dried. The proximate analysis and protein yield were measured. Traditional alkaline extraction was used as a control under optimized conditions. So it turned out that the highest yield of pea protein isolate reaches to 82.6% at ratio at 1 to 11.5, pH 9.6, extraction time at 13.5 minutes with 33.7% ultrasonic amplitude. The structural and functional properties were evaluated using surface hydrophobicity, SDS page, solubility, gel formation capacity, emulsification capacity, and stability. The authors, they also did FTIR, amino acid composition, forming capacity, stability, water, oil, bending capacity. Due to the time, we won't cover those in our presentation. Now, let's take a look at the surface hydrophobicity data. Based on what we learned in the class, we know that ANS agents bend through hydrophobic interactions with hydrophobic surface of the protein. So the more hydrophobic residues are on the surface, the more ANS will bend and we'll get more fluoric acid data. The graph gives the surface hydrophobicity data for both PPI extracted by traditional alkaline extraction method, which they label here AEPPI, and also by the ultrasound assisted alkaline method AEPPI under different extraction time. So we can see that ultrasound significantly improved surface hydrophobicity. That is because the ultrasound treatment changed the protein structure, so more hydrophobic groups were exposed. That's why we got a higher surface hydrophobicity data. However, we couldn't observe the significant changes in surface hydrophobicity of the PPI that's extracted by the traditional alkaline extraction. The protein profile of PPI treated with and without ultrasound was determined by the SDS page under reducing and non-reducing conditions. Overall, all PPI proteins contain bands identified as convaseline, vaseline, and legumin. So convaseline, which are at around 70 kilodalton, and vaseline at around 50 kilodalton, were identical under reducing and non-reducing conditions. That's because they do not contain any disulfide linkages. However, we see that legumin at about 60 kilodalton, which was broken up into the acidic and basic subunits under reducing and non-reducing conditions. So there were no other significant difference between the PPIs, which suggests that ultrasound treatment did not break disulfide bonds or cause subunions of fractionation under reducing or non-reducing conditions. As for the solubility, the minimum solubilities of non-treated sample and ultrasound-treated sample were observed at pH 4.5, which is close to the isoelectric point of the protein. So at this point, the protein lose their charges and also lose the repulsion. So at the same time, getting more surface hydrophobicity interactions and protein aggregates. That's why we got the lowest solubility data at this point. Generally, the ultrasound-treated sample has higher solubility than the non-treated sample at the same pH. So the decreasing of the particle size from the ultrasound treatment improved the protein and water interaction. Finally, let's take a look at the emulsification and gel formation capacity. We can see from the table here that both emulsification activity and emulsification stability of ultrasound treated samples were higher than those without treatment. That is because the ultrasound treatment improves the molecular flexibility and surface hydrophobicity. So the protein molecules could be adsorbed at oil-water interface more efficiently. And here, the least gelation capacity of the ultrasound-treated samples decreased by 15.4% compared with those without treatment. So the higher surface hydrophobicity in the ultrasound samples might be one of the reasons that give it better gelling ability. Here are our conclusions for the first article. So the highest extraction yield, about 82.6% of the pea protein were achieved. And also we can see that the ultrasound assisted alkaline extraction method caused structural changes and improved the functional properties of the pea protein.
Comes the second article. Functional attribute of pea protein isolates prepared using different extraction methods and cultivars. Here we have three methods. The first one is alkali extraction isoelectric precipitation. So the key point here, we have to use pH solubilization and then pH precipitation and freeze drying. So we learn from the class, PI is around 4.5, and that's why now here the author has just used that value. Alkaline extraction, the purity is around 85%, yield is around 69%. Salt extraction, here the key point is the pH stabilization, and also we have to use the dialysis membrane for the specified cutoff molecular weight. The results are extraction purity is around 75.6%, yields around 72%. Micellar precipitation. Here in micellar precipitation, the first step is just for solubilization, and then centrifugation, protein concentration, and freeze drying. The result are as follows. Micellar precipitation. Yield is around 85.2%. Sorry, yield is around 30.9%, and then the purity is around 85%. Yes. Now, for the next step, we have to study structure analysis and functional analysis. We start with the structure evaluation. So, surface hydrophobicity. The P globulin fraction had higher surface hydrophobicity than albumin fraction. From the data, we can see alkaline extraction has high surface hydrophobicity than salt extraction and micellar precipitation. It is hypothesized that alkaline extraction gave high surface hydrophobicity because this method of extraction precipitates mainly globulin protein, when salt extraction precipitate both globulin and albumin. Zeta potential. We learned from the class, zeta potential is not always negative. Under these conditions of pH, electrostatic repulsive forces between neighboring protein in solution would be expected to be low, leading to a possible increase in protein-protein interaction and aggregation. The surface charge for all protein, as you can see, was similar regardless of the method of extraction or cultivars. The value are around minus 21 millivolt. Next, we talk about functional evaluation. This step, we talk about solubility, we talk about emulsion capacity and emulsion stability. Solubility. That was being tested at page 7. Solubility here is related to folding of the protein and exposure of hydrophobic versus hydrophilic groups. The result for hydrophobic groups, they result in protein-protein interaction and insolubility. The lower solubility of alkaline extraction and visceral protein may be due to protein-protein hydrophobic interactions that occur during that period of time, preventing the protein from interacting with the solvent to promote hydration and solubility. Salt extraction produces isolate with the highest solubility between 85 and 91%, followed by alkaline extraction and visceral precipitate. Emulsion capacity. The salt extraction cultivars had better emulsification capacity compared with the alkaline extraction. But since Stone, the author of the article, didn't clearly present the statistical analysis in this result, so it is difficult to tell if this difference is significant or not. Emulsion stability. Emulsion stability for all 9 isolates had high emulsion stability, which is higher than 96%. Under the conditions tested, indicating that the droplet were successfully dispersed throughout the water phase, mainly because of the following reasons. The first one is adequate strength of viscoelastic film at the interface, as well as sufficient charge inclusion. And second one is steering hydrants between droplets to prevent coalescence of the droplet. No data was obtained for visceral precipitation relating to emulsion capacity, but they had the highest ES value. We will address this in our critics. As conclusion for this article, salt extraction produced isolate with the best result overall, with the highest yield of almost 72% and functionality regardless of cultivar. All extraction produced isolate that successfully stabilized the 50-50 water oil emission when only salt extraction and alkaline extraction isolate had emission capacity properties.
Okay, so at this point, we're going to talk about our third and final paper, which was a structure and function guided extraction of pea protein isolate, and also featured the scale up of this pea protein extraction. So Hansen evaluated 2 different types of extraction methods. The first we're going to cover is an alkaline isoelectric precipitation, which was similar to what Stone had done in the previous paper, but instead Hansen did a double solubilization at a more mild pH of 7.5. So that means when we precipitate the proteins at their isoelectric point of 4.5, they came into the supernatant, and then they were centrifuged, and that supernatant was neutralized. The proteins were then collected concentrated using dialysis with 3.5 kilodalton cutoff, and then freeze-dried. So the purity from this extraction was 84.9%, and it had a yield of 69.9%. The next extraction method that Hansen evaluated was a salt solubilization extraction method coupled with membrane filtration. And this technique used a 0.5 molar NaCl solution to solubilize the pea flour. This increases that charge load on the proteins and causes them to be repelled from one another and then interact more with the water. So in the end, after centrifugation, the proteins are in the supernatant. The proteins are then neutralized and they undergo ultrafiltration or diafiltration to concentrate and then help remove that excess salt. And then after that, they're freeze-dried. So the purity for the salt extraction was 92.8% and the yield for this extraction was 72%. So let's talk about some of the methods that this paper used. So surface height for structure analysis, we looked at surface hydrophobicity, surface charge, denaturation temp, SDS page for molecular weight, and then also size exclusion HPLC. And then for functional analysis, solubility, gel strength, emulsion capacity, and then emulsification activity and stability were evaluated. But for the sake of time in this presentation, we're not going to cover the size exclusion HPLC or the emulsification activity and stability. And it should also be noted again that this was the only paper to actually explore scale up of these extraction methods. But for the sake of time, we're not going to cover the results of that. So let's start with some structural evaluation with our SDS page. And very quickly, I just want to go through the lineup of our gel here. So row or column 1 is going to be our molecular weight markers. Column 2, our pH extract. Column 3, our salt. Column 4, our scale up. 5, scale up salt. 6, our commercial P, and 7, our commercial soy. And that's in both non-reducing and reducing sections. So one thing that these researchers found is they found unique bands at 25 and 9 kilodaltons in the salt PPI. So that's column 3 that weren't present, or if they were present, they were very faint and faded in the pH PPI. And so they're thinking that this is due to the nature of the isoelectric precipitation that happened with the pH extraction. So at pH 4.5, we were able to precipitate these proteins, but this isoelectric point isn't inclusive of albumin proteins, which have an isoelectric point of 5.5 to 6. So basically they were discarded and they just were discarded with the supernatant and remained soluble there. The difference is with the salt extract, they were able to be kept. So that's the presence that we're seeing there. So evidence of this preservation is definitely a win in the eyes of a salt extraction. And those are seen in both non-reducing and reducing conditions. Next, we're going to talk about denaturation temperature. And as expected, the harsh processing that we see with that commercial pea protein isolate resulted in no notable denaturation peaks. But the viscolin and legumin fractions of the salt PPI did have a higher denaturation temperature compared to the pH PPI. So that speaks to the fact that the salt extraction was less denaturing than the pH one. And obviously both of these benchtop methods were less denaturing than the commercial. Now let's look at surface hydrophobicity. There wasn't a significant difference between the surface hydrophobicity for the pH and the salt extraction, but there was a notable difference between the surface hydrophobicity from the benchtop extractions and the commercial pea protein isolate. And so we're thinking that more denatured state of that commercial isolate resulted in exposure of more of those hydrophobic interiors, thus giving a higher surface hydrophobicity. Oops, excuse me. And now we're going to look at our surface charge. So there is a significant difference between the surface charge of the pH and the salt extract, with the salt extract having a less negative surface charge. So these differences may be due to like protein composition. And as I mentioned in that SDS slide before, we have the presence of those albumin proteins in the salt extract. So that would contribute to that. And now we're going to look at our functional evaluation. So starting with solubility, which was evaluated at pH 7 and 3.4. and also under heated and non-heated conditions. And the point of that was to kind of mimic solubility in acidic or neutral situations, and as well see what the protein would do if it underwent any processing, heat processing. So at pH 7, the pH isolate had better solubility compared to the salt extract. And the higher surface charge of that pH extract was probably what contributed to this. At pH 3.4, we can see that the salt extract had a higher solubility when heated and non-heated, and Hansen reasoned that this was due to the greater denaturation state of that pH extract. And then, as we know from class, like this denaturation and this unfolding is going to reveal those hydrophobic interiors and reduce solubility. So that's likely what happened there at pH 3.4. And then it should be noted that both the salt and the pH extracts, the benchtop extractions, they both performed better and had better solubility compared to the commercial pea protein isolate. Now we're going to look at gel strength. So for gel strength, the salt PPI outperformed the pH PPI significantly, and it was actually reaching close to the gel strength of the commercial soy protein isolate, which is a great thing. We're thinking that the slightly lower surface charge and then the lower surface hydrophobicity in that salt protein extract resulted in this. And it resulted in more balance between the hydrophilic and hydrophobic interiors of the proteins. And then, that supports better gel formation because that balance is important for that. And now we're going to look at our emulsification capacity. So for emulsification, the salt and the pH were comparable. There weren't any notable differences there, but when you compare this to the commercial protein isolate, you can see that there is a significant difference, which shows that the emulsification capacity of the benchtop extracts did improve, like that extraction technique did improve the emulsification capacity of the benchtop extracts. Okay. So our conclusions. As you can see from the comparison of the results for the salt extract to the pH, the salt did have a better yield with a yield of 92.8% and a purity, of 92.8% and a yield of 72.0%. This paper also found that extraction at close to neutral pH coupled with double solubilization is feasible, and it can result in good protein with preserved structure and functionality. This paper also found that salt extraction coupled with membrane filtration is an industry feasible method. And again, it also preserves the protein functionality and structure. And then finally, we didn't cover this in this presentation, but the scalability of these extraction methods was observed and confirmed. So that's going to help guide industry as we continue to make pea protein a more functional food ingredient.
Overall conclusion. Here you can see ultrasound assisted extraction from different authors. Now this is the conclusions we have just concluded. You can see the result about based on pH, based on purity and the yield. So difference in purity between those methods may be due to the type of filtration used. Stone and Wang used high alkalinity. Hansen proved that wide techniques can produce comparable results. What about salt extractions? So we can see also different authors, different results in terms of purity, in terms of yield. You can just see just from the table, from the projector over there. Hansen has used different types of salt. He used sodium chloride. Stone has used two types of salt. One, the buffer, which is mixed of different types of salt. And for misera precipitation, he has used sodium chloride with high concentration based compared with salt extraction for the first data. Critics and suggestions. Positive critics throughout consideration of outside influences. Each paper compared extraction method through structural and functional analysis. consideration of how P cultivars could change extraction results. Negative critics. One in stone could use additional structural and functional analysis to support their findings. One in Hansen. Optimize the extraction method. Stone did it. Industry feasibility of method was not discussed in Wang and Stone's papers. Stone didn't clearly present statistical analysis in their results table, making it difficult to compare the data.
Any questions?
Great, good, thank you. All right, go ahead and-
When we're salt extraction not even there, but the everything's gonna seem like that was the best overall. Is there like is there like an application more time to be looking for salt extraction for protein?
Yeah, doesn't take this. I think there definitely is applications where you wouldn't want a salt extraction for pea protein, but I guess you would have to be sure of what that application is first. I think that's most important because both of them have pros and cons. You know what I mean? So, yeah.
So what is the cons of using salt extraction?
I think that one of the cons that we found through Hansen's paper was disproved was the industry feasibility. So the environmental impacts of using so much water and such. Another thing that we noticed was differences in functionality. So I want to go back perhaps here. So the solubilities are different. So depending on what kind of application, like if it's a beverage, perhaps you would want to use a pH extracted pea protein isolate instead of a salt extracted if you want that solubility at that pH. So there are those kind of considerations, but I do think that the application is really gonna rule which extraction method you would use. And that's not just with the salt extraction and pH. I am also thinking about the ultrasound assisted as well as my cellular.
So I'm just gonna challenge a little bit the fact that you said that salt extraction might not be great from an environment. And was what did Hansen do specifically to overcome the effect of using a lot of water?
Yeah, that would be the membrane filtration. And then also optimizing the amount, like the protein, the amount of protein that's being solubilized with the salt would also do it too. So that helped a lot. And Hansen actually optimized this. And so when we were looking at Stone's work, we didn't see that optimization. So I think that definitely made a difference. And that was a point that Hansen proved.
Yeah. What other way if they didn't use membrane, what would that be another way to purify the protein using the salt?
If thus we go back to Stones, he has used the dialysis membrane. So dialysis
If
membrane.
you don't use membrane, what is another way of concentrating the protein based on what we've covered in the past? That is not environmentally good.
Could you use, I mean, I guess, no, never mind.
Remember,
Chromatography.
so the concept we learned in class, soaking in and soaking out. So in industry, they don't do salt extraction just because the way to concentrate the protein is using more salt than just taking it out. So with that research, what Hansen did is use membrane filtration instead of having high concentration of salt. So you don't need as much water to clean and wash the salt. So to answer now, what
You asked, was that it is feasible, it is sustainable, it is all that, that's what. Okay, but and each one of you, and I'm not gonna ask by name, so you should all prepare one question, so go ahead and ask the question. Go ahead.
I was just curious why there was a one DC results for the, my cellular precipitation.
Yeah, that's a good question. We'll also try to figure out why they have ES data, but they do not have the EC data.
Yeah.
To be honest, the paper didn't really mention that part clearly, so we don't really like understand why they have ES but without EC.
Yeah. The paper presented other like referencing articles or, that did support the emulsification stability of the micellar precipitation, but their own data itself didn't back it up. So, and they didn't provide explanation of that. So that was definitely poorly done. Yeah, so
Okay, and at the same time, they also didn't provide stuff, did they explain why they didn't provide stuff?
They actually did provide, they said they did statistical analysis, but they just didn't like make it clear in that result table.
But basically, there's no.
Yeah, we cannot, like, it's really hard to know which one has the significant difference than the other.
Why do you see very much lower solubility for micellar precipitation compared to the other?
Yeah.
So, we found out micellar precipitation P protein as what may be due to the protein hydrophobic interaction that occur. And then they prevent protein from interacting with the solvent to promote hydration and solubility.
But what was the surface solubility of the micellar from that? It wasn't high compared to alkaline.
No, it was lower. Alkaline was higher.
Okay, so surface hydrophobic was not the cause for the lower solubility that you see. For micellar precipitation. Any thoughts on that?
I'm wondering if that could be by nature of the extraction method, because it's solubilizing in that buffer salt solution for 72 hours. And I was thinking that might be nature of the protein, which might cause some of that, but honestly, I didn't find anything specific in the paper for that. I don't know if you guys. No, they didn't measure DSC.
So
Did they measure
I believe they did.
I think they only measure moisture content.
Only moisture in this one. Okay.
another factor.
Yeah, this paper was definitely lagging.
Another factor that we can also consider is they use one concentration of salt. If maybe we have used maybe different concentrations to see which one is the best one, maybe in that case you can say the blood maybe can be compared, say, okay, maybe the value you get can be a little bit higher.
Yeah, I'm trying to just see why they saw
Yeah.
lower solubility.
Yeah,
So
they only measured moisture, not ash.
Okay, so for the sake of the class on 10, they didn't do the denaturation, so we cannot tell. They didn't look at the they have a CSP.
No.
So we don't know the degree of colonization. So that is gassy, and we don't know the ash content, so if it's high in salt.
Yes.
After, did they do any dialysis?
Not with this method, the bicellular.
Yes.
I don't believe they did.
To go back one.
Yeah.
So they didn't do any membrane of dialysis.
No.
So they must have really high salt concentration in the end. Which caused it to be not to have
Probably just the protein has been shared
Yeah, that's
with
true.
the hypostatic salt. So that prevents just interaction with salt.
Okay, one more question from you.
So,
So I have a question that I didn't understand what is my, precipitation, what does it even mean, right?
yeah. So basically, so it shows here, like they use the salt solutions to try to solubilize their samples, and then they kind of centrifuge it and collect the protein to collect the, like they solubilize the protein into supernatant, and later they will have that supernatant, and then they dilute that supernatant with the salt solution again. That is it. And after that, they do centrifuging to collect that protein.
Yeah.
Yeah.
Okay, that explains my cellular precipitation. So what they did something, same thing we do when we do salt extraction. So they put in some salt so that you can solubilize the globulin proteins. So that's the first step. So now your protein is solubilized, and then you precipitate the non-soluble once the fiber starts. Then you have your soluble with the salt. They take that, when they dilute it, you're bringing down the salt concentration. You dilute it, so the globulin protein are no longer soluble because you dilute the salt. So then they provide. It's like an inverse, so you solubilize, and then the inverse is solubilization. So the first part refers globulin, because globulins are soluble in salt. And then when you dilute it, you're reducing the salt concentration, so you are removing that salt in the fat. So, yeah. So it's kind of inverse. Okay, so we went over, I appreciate everybody's patience, and I'll take the blame for forgetting this. Please, hands in your evaluation sheets, and I'll wait for you to evaluate the child and do that. Okay. Thank you, guys. Thank you.
Way to bring
Oh, that's good. Okay, see you. More obviously, more effective by the yeah. Yeah. It's more time for us and then work, so can they grant it?
That's right. As a group, you know, as a as a team. Yeah, that's-
Ma'am, you would have reached out to groups if their presentation date got moved, right?
Yeah, I reached out to two groups already.
Okay.
The others, I'm not sure yet, depending how I move. I'll let you guys know
Yeah.
ahead of time,
Okay.
depending on the lectures, the makeup lecture and the lecture after that. After I know that week where I'm at, I'll let you guys know.
That sounds good. All right.
Thank you. Oh, yeah, fine. Oh, good. Have a good night.